Now we can start looking at circuits, AC circuits, and the two things that we want to try to do when we're doing AC circuits is we want to stay away from differential equations, and I think everybody can agree that would be a good thing. But if we're going to stay away from differential equations, we want to be able to use what we know, and so we'd like to be able to model the circuit like a DC circuit, so that we can use Kirchhoff's voltage law and Kirchhoff's current law. So what we want to do is wait until the circuit is past all the transients. So when you first turn on the circuit, the capacitors are not charged, the inductors are not charged, and at the very beginning you get these unsettled states, and those are called transients, and then they eventually die out as everything starts to and when everything starts to settle down. And so you get these transients, and then the circuit will get stable. And this could be the voltage across a capacitor or an inductor. And so it's this part where your transients are that you're avoiding. You're looking at what's called steady state. And this is the part that we're more interested in at the moment. So for AC circuits, we've used these definitions previously for the voltage, and we were saying, well, voltage is just some max voltage times cosine, and we're going to make this general. We're just going to say omega t plus some phi. And for the current, it was very much the same. Some max current times cosine of omega t plus phi. And we can put these into RMS values, which we're going to have voltage RMS times the square root of 2. And remember that cosine, you can have 2 pi frequency t plus phi. And for the current, we're going to have IRMS times the square root of 2 times the cosine of 2 pi frequency times time plus phi. Now, in these forms, it's not very useful to me, so we're going to convert these into a different form. But before we do that, let's think about, well, if I have an AC circuit, I'd like to be able to have this general way of doing it, and I want to stay away from sines and cosines. Well, what we can do is look at how we convert our components, and then we can come up with a way of being able to represent these voltages and currents. Well, let's start by changing our voltage supply to the Euler equivalent. And also our current. And now we can go through and do our definitions for resistance. I want to go to the next page so I have a little bit of room. So resistance is just voltage divided by current, and that's just going to be V naught E to the j omega t divided by I naught E to the j omega t, and the E j omega t at the top and the E j omega t at the bottom are going to cancel out, and that just gets me that the resistance is equal to V naught over I naught, and this is in the case of AC, so these voltages are changing, but the resistance is always this ratio. So we see that resistance in AC and in DC have the same relationship. Now let's look at the inductor. Well, we know that for the inductor, the potential, the voltage across the inductor, is related to the inductance times the derivative of the current. So if we put this relationship into our function here and put I over here, I'm going to have potential is equal to L d over dt of I naught E to the j omega t, and I want to put in my voltage here. I'm going to change my voltage function here. So it's going to be V naught E to the j omega t. And if I take and do the derivative, I'm going to have j omega L times I naught E to the j omega t. And if I solve for a relationship like we had for voltage, then I'm going to have V naught E to the j omega t over I naught E to the j omega t. So in like resistance, we had some voltage divided by current. Here I have a voltage divided by a current, and I'm left with j omega L. This e to the j omega t on the right side is very similar here, but we have this imaginary number here, j, that is not really a resistance. So we define it as a new variable. We call it reactance. We use the variable x. We'll put a subscript L so that we know that it's inductive reactance. And that inductive reactance is equal to j omega L. Now sometimes we'll write it as JXL, and in that case that's just going to be omega L if we do that. Sometimes we try to simplify things down. We do calculations, and I'm going to show you why here shortly. Now for capacitors, we have the relationship that the current is equal to the charge times the derivative of the potential. And we get that because we have charge is equal to capacitance times voltage. If I take the derivative of Q, I take the derivative of the voltage. And now I put in my Euler representation. And I need the voltage divided by current, and I want to put everything else on the other side. So I get V naught e to the j omega t over I naught e to the j omega t, and this is equal to 1 over j omega c, and that's just equal to negative j divided by omega c. And this is our term for capacitive reactance. Now the consequences of this, and the reason why we have these imaginary numbers, is because inductors and capacitors store energy. And you can't change energy instantly. In the case of the capacitor, it's the form of an electric field, and you have a charge that is on the plates that will give you this electric field. You can't move this charge instantly. It takes time to be able to move it off of the plates. And for an inductor, well, it's the magnetic field. And that's related to the current, and we have Lenz's law. So this J represents the fact that you cannot change the energy that is stored in the capacitor and in the inductor rapidly. So the AC potential that's across the circuit, it's always constantly changing. It's a constant sine wave, but these can't change. So what ends up happening is you have three different possibilities. One possibility is with the resistance, and there's no what we call phase shift. Which says that if I have a signal, then if I have this, the black is voltage, the current is going to be exactly on top of the potential. They're going to happen, the changes are going to happen at the same time. For the inductor, we're going to have a 90-degree shift with the voltage. The voltage is going to lead the current. And to remember this, we say Eli. Voltage leads current, and the L being the inductor, E being voltage, I being current. And when we look at this on a graph, then if I have the potential, I'm going to have it in this direction for the moment. Then the current is going to lead, the voltage is going to lead the current by 90 degrees. So I'm going to have a current that will I drew this wrong. Drew this a little bit off here. Let me redo this. So it's going to lead. So the voltage is black, the black color here. And the current is red. For the capacitor, well, you can guess that current leads voltage, and we can think of ice, and if we graph that out, it will look something similar to this. So, because of the leading and lagging of the currents in the inductor and capacitor, we have these phase shift, and this is due to the energy not being able to change instantly. And to remember the sequence of what leads what, we use Eli likes ice. That helps us to remember our relationships of what leads what depending on the inductor or the capacitor. So now we're ready to get into how to solve an AC circuit. So in the next step we're going to go over the next video we're going to go over the steps that we need to follow to be able to do an analysis.